In this lecture, we are going to discuss a very popular topic in modern deep learning, GANs. GAN stands for Generative Adversarial Network. Yann LeCun, who is one of the forefathers of deep learning, described GANs as the most interesting idea in machine learning in the past 10 years. By the way, this is also who the famous LeNet architecture of convolutional neural networks was named after, the CNN from which all other CNNs are based. Ian Goodfellow, the inventor of GANs, is now himself a prominent deep learning researcher. My goal in this lecture is to introduce you to the fundamental theory behind GANs. You'll see that, although they sound complicated, they are nothing but a new and interesting way of combining things we already know how to build. This is a common pattern in deep learning. Neural networks themselves are nothing but a bunch of logistic regressions chained together. CNNs and RNNs are nothing but neural networks with shared weights. I like this approach because deep learning allows us to build tons of cool things with only a few simple tools and some creativity. First, let's discuss what GANs are even used for in the first place, since this may not be immediately obvious. The main use case for GANs is to generate data. 99% of the time, this means generating images. The reason GANs have become so popular is because unlike the models that came before it, GANs are exceptionally good at this. Here are some example images produced by state-of-the-art GANs. Believe it or not, these are not real people, but rather images generated by a computer. One thing you can do, if you want to see a few more examples and observe for yourself the power of GANs, is to check out a few websites that display such examples. One website is thispersondoesnotexist.com. This one is simple. You go to the page and it shows you a randomly generated face. You can refresh the page to see more faces. Another one which I really like is whichfacesreal.com. This one is more like a game. So you're shown two images, and one is real, one is fake, and you have to pick the right one. So check these out for yourself if you want to see more examples of how good GANs are at generating realistic images. Okay, so what's the main idea behind GANs? GANs are a system of two neural networks, each of which has their own objective. The objective of the first neural network is to generate images. The objective of the second neural network is to discriminate between real and fake images. This is all you need to understand how GANs get their name. They are generative because you are generating images. They are adversarial because you have two neural networks which oppose each other in an adversarial manner. They have opposite goals. The goal of the first neural network is to generate images that look real, and the goal of the second neural network is to detect real and fake images. Intuitively, you can think of GANs like a counterfeiter and a shop owner. The counterfeiter goes to the shop and tries to use fake cash to buy an item. The shop owner has to detect whether the cash being given by customers is real or fake. Perhaps at the beginning, both the counterfeiter and the shop owner are not experts at what they do. The counterfeiter is not that good at making fake bills, but the shop owner is also not that good at detecting fake bills. However, once the shop owner learns to detect the fakes, the counterfeiter may then improve on his counterfeit design and trick the shop owner once more. After a while, the shop owner may again realize he is being duped and learn to inspect the bills more carefully to detect these improved fake bills. The cycle continues as the counterfeiter gets better at tricking the shop owner and the shop owner gets better at avoiding being tricked. Of course, these analogies only take us so far. How do we actually build a GAN? Let's recall all the ingredients we need for a basic neural network that we want to train. First, we need a neural network. That much is obvious. Well, in our case, we actually have two neural networks. In order to train the neural network, we need an objective or a loss function. This is the big question with GANs. What is the loss function? But once we have these two things, everything else is nearly trivial. We call model.fit, which does gradient descent, and that's that. Okay, so let's dig a little deeper on what the loss function is. In fact, for GANs, we're going to have two loss functions, one for the generator and one for the discriminator. Let's first look at the discriminator, since that's more in line with what we are used to already. Since the discriminator must be able to tell the difference between real and fake images, this is a binary classification problem. For every input, the discriminator can only predict one of two categories, real or fake. As you know, for binary classification, the correct loss function is the binary cross entropy. What about for the generator? What is the loss function? This is what I call applying creativity to the basic tools that we already know about. Intuitively, the basic idea is this. We have our generator network, and our generator network feeds into our discriminator network. From this perspective, this is just one gigantic neural network. What we can do is, just like with transfer learning, we can freeze the layers in the discriminator so that when we run gradient descent, only the generator network gets trained. Next, and here is the ingenious part, we want the generator to get better at producing real-looking images. And so our loss function will remain the binary cross entropy, except that we are going to switch the labels. In other words, let's say for the discriminator, real is 1 and fake is 0. We're going to pass in fake images, but make the target 1, such that we're encouraging the discriminator to identify these fake images as real. But the discriminator weights are frozen, so they won't change when we do this. Only the generator weights are trained. Here's what the loss would look like, mathematically, if you're interested. Here, all the y-hats are predictions on fake images, since the generator is now the input into the discriminator. Because we always want the target to be 1, we only care about the first half of the binary cross entropy. So essentially, it's just the sum over the log of all the y-hats. Or stated another way, the negative log likelihood of the y-hats. Now that you understand the basics of how GANs work, let's look at some details that will help us in our implementation. We know that neural networks must have both inputs and outputs. For the discriminator, this is easy. The input is an image, and the output is a prediction about whether the input image is real or fake. For the generator, this will be a little strange. We know that the output should be an image because its job is to generate images. But what is its input? In fact, the input to the generator is nothing but noise. What we are going to do is generate noise from a multivariate standard normal, and the generator will learn to map this noise to an image. Mathematically, what we are doing is saying, we have some random vector z, which comes from a standard normal. Let's say it has size d equals 100, although this is a hyperparameter, so you can choose what you like. We call this 100-dimensional space the latent space. In essence, you can think of it as an imaginary space where the generator believes all the images of digits live. So maybe the 1s are over here. All the 7s are right beside it because 7s kind of look like 1s. Near the 7s are the 9s because 9s look like 7s if you draw the loop very small. So you can see how these images kind of morph into one another when they are drawn in different ways. So this latent space maps all the different kinds of images that you can have. And of course, this is a source of confusion for both computers and humans. When an image is right on the boundary between, say, 7 and 1, it's difficult for us to tell what digit it should be. Should it be a 7 or should it be a 1? In any case, what the generator is doing is, it's learning to associate each part of the latent space with different images in a continuous manner. Then later, when we generate images, we're just picking a random part of the space and generating an image from whatever that part of the space represents. You can think of the generator as kind of the reverse of a feature transformer or an embedding. With a feature transformer or an embedding, we're taking an input image or an input text or some other kind of input, and we're mapping it to a vector. But for a generator in a GAN, we're doing the opposite. We start with a vector, and then we map that to an image. As always, it's going to be helpful to look at some pseudocode before we move on to the actual implementation. So here's how it's going to look. So the first step is to load in our dataset. We're going to use MNIST for this example. In future courses, you'll learn about more advanced types of GANs, which will work on more complex types of data. Next, we're going to create our discriminator and generator networks. These are just standard neural networks, some dense layers, some ReLUs, and so forth. The trick is, we're going to have two optimizers. One that optimizes the parameters of the discriminator, and one that optimizes the parameters of the generator. Conceptually, you can imagine that the loss function is always applied to the output of the discriminator only. In either case, we will use the binary cross entropy, but with flipped labels. When we train the discriminator, half of the data will be real images from the dataset, and half of the images will be generated from the generator. These will use the true labels. When we train the generator, we will generate random noise, pass that through the generator, then pass that through the discriminator, and use a flipped label, meaning that we say it's a 1 even though it's really a 0. We can conceptualize this chain of generator and discriminator as a kind of combined model, where only the generator weights our parameters. Although that's not exactly how it will look in code, it's a good conceptual tool. Once we've built our two networks, we're going to run a gradient descent loop as usual. Inside the loop, we're going to train the discriminator and generator in alternating order. In order to train the discriminator, we'll grab a random sample of images from our dataset and a random sample of images from our generator. Then we'll do one iteration of gradient descent by calling discriminator.trainOnBatch. We do this for both the real and fake images. Then, for generator training, we'll do the following. First, we'll generate a batch of noise samples. Then we'll call combinedModel.trainOnBatch, passing in the noise and ones for the target, to do one iteration of gradient descent on the generator. After several thousand iterations, our generator should be good enough to produce images that look like the MNIST dataset. As a final note for this lecture, I want to mention that, in terms of model evaluation, we're going to take a bit of a departure from what we normally do. You'll recall that for most models, what we're looking for after training is that the loss goes down and the accuracy goes up. This makes sense if you were doing classification or regression. But now we are no longer doing classification or regression. Remember that in our case, the generator and discriminator are constantly trying to one-up each other. And so what is interesting is that the loss functions for both the generator and discriminator should look just like noise. It should appear that, if you only look at the loss per iteration, that nothing is happening at all. But in fact, something profound is happening. Both the generator and discriminator are improving. You don't see this in the loss per iteration because ideally, both the generator and discriminator are improving at the same rate. Let's now summarize everything you learned in this lecture. First, you learned that GANs are not just a single neural network, but a system of two neural networks, a generator and a discriminator. The discriminator is responsible for telling the difference between real and fake images. The generator is responsible for creating realistic-looking images. Both the generator and discriminator learn in tandem. The loss function for the discriminator is just the binary cross-entropy because there are two classes, real and fake. The loss function for the generator is not directly applied to the generator, but rather a combined model where the generator feeds into the discriminator. This allows us to, again, use the binary cross-entropy, but there are two important details. First, we freeze the weights of the discriminator so that only the generator is trained. Second, we flip the labels so that images generated by the generator are labeled as real. Next, we learn that the input to the generator is nothing but noise, sampled from the latent space. The latent space is where the encodings for each digit lives. You can think of this as the opposite of a feature transformation or an embedding. An embedding or feature transformation is like a mapping from an input image or an input word or any other kind of input into a single vector. The generator does the opposite. It takes a vector, which lives in the latent space or the embedding space, and produces an image. Lastly, we learned that when training GANs, the loss per iteration should not be informative in the sense that it should not decrease over time, as it does when we are training other models. This is because both the discriminator and the generator should be learning at the same rate, continually helping each other improve. In this lecture, we're going to take a closer look at how the GAN code will work, and hopefully iron out a few details before we move on to the actual notebook. This is another interesting model in this course, because unlike all the other algorithms we looked at, now we're dealing with two neural networks simultaneously, rather than just one. So it's kind of an odd concept. What I want to focus on in this lecture are a few overarching themes. First, we'll look at the architecture of each model. Just for fun, we'll use a few more advanced layers and activation functions that we didn't use earlier in the course. Second, we'll look at how to train the model. This is the centerpiece of this section, because unlike all the previous examples you saw in this course, this training loop will be very different from what you saw before. You may have assumed that, because the generator is a kind of anti-discriminator, that they would have opposite architectures. What I mean by that is, if the generator had hidden sizes of 100, 300, and 784, that the discriminator would have hidden sizes of 784, 300, and 100. In fact, this need not be the case. In our example, we'll make the generator a more powerful model than the discriminator. The intuition is, binary classification is an easy task, whereas generating images is a hard task. For the discriminator, all you have to do is map the input to 0 or 1. There aren't that many degrees of freedom. For the generator, you have to generate 784 different pixel values, and they all have to be coherent, so there are many degrees of freedom. So that's the idea. Generating is hard, but discriminating is easy. So here's what we'll be using for the discriminator, although you should feel free to play around and design your own. It's just a series of linear layers followed by leaky ReLUs. Recall that a leaky ReLU is just like a normal ReLU, except it has a small positive slope for values less than 0. This is an attempt to avoid the problem of dead neurons, where the slope becomes 0, and therefore the gradient becomes 0, and therefore no error can backpropagate. Here's what the generator looks like. Again, feel free to play around. So, in addition to leaky ReLUs and linear layers, we'll also add batch norm to the mix. We've also added a tanh activation at the end, which implies that we'll be working with images in the range -1 + 1 rather than 0 to 1. Experimentally, researchers have found that these changes tend to yield better results. Okay, so here's the real meat of this code. After we define the discriminator D and the generator G, we're going to define the loss and optimizer. The loss is just the usual binary cross entropy, but we're going to have two separate optimizers, one for each network. You'll notice that when we instantiate the optimizers, we only pass in the parameters that we want the optimizer to update. So when we call dOptimizer.step, it's only going to update the parameters of the discriminator. When we call gOptimizer.step, it's only going to update the parameters in the generator. Inside the training block, we're going to start by instantiating constant arrays to store zeros and ones. These will act as our targets, so we don't have to keep creating new arrays on each iteration of the training loop. Inside the training loop, we're going to loop over the data loader. Remember that we don't need the image labels, so we can use an underscore to ignore them. What we're going to do now is 2 training blocks, one for the discriminator and one for the generator. This slide will focus on the discriminator. Now, one question you probably have is, does it matter which order you train them in, the discriminator first or the generator first? I would recommend you try it out as an experiment. So how do we train the discriminator? First, we start by passing real images into the discriminator. That's just the outputs from the data loader. From this, we can calculate the loss using the ones target. For the fake images, we start by generating a batch of random noise and then passing that through the generator. From that, we get fake images, which we then pass through the discriminator, and from that we get fake outputs. We pass the fake outputs through the loss function using the zeros target. Next, we take the average of the 2 losses to get a single value we can optimize. After this, we would like to call dloss.backward and doptimizer.step, but before that, we have to remember to zero the gradients. Next, let's look at the generator training block. One interesting technique discovered by researchers was that doing multiple steps of training for the generator for each single step of the discriminator seemed to work well. This goes along with our theme that the generator is harder to optimize than the discriminator. Therefore, it requires more training. So to accomplish that, we can just do a loop. Inside the loop, we generate some fake images once again, using a batch of latent noise, and passing this through the generator. Since this is for training the generator, there is no need to use any real images. We just pass the fake images through the discriminator, and then pass that output through the loss. Importantly, this time, we use the ones target to tell the loss function that we want the weights to go towards these images being classified as real. Next, we zero the gradients and do a gradient descent step as usual. In this lecture, we are going to look at how to implement a GAN in code. This lecture is going to walk you through a prepared Colab notebook, although a very good exercise, which I always recommend, is once you know how this is done, to try and recreate it yourself with as few references as possible. As usual, you can look at the title of the notebook to determine what notebook we are currently looking at. So at the top we have all our usual imports. We've also imported the save image function from Torch Vision, which is a useful utility for saving an entire batch of images to a single image file. This will let us check how our model progresses over each iteration. Next, we define a set of transformations to perform on the data. Remember that researchers have found that using pixel values in the range -1 to +1 tends to work better. So this code might seem strange at first, but if you check the calculation, you can verify that it works. First, remember that the 2 tensor transformation already scales the image to be between 0 and 1. So if we take 1, subtract a mean of 0.5, and divide by a standard deviation of 0.5, we get 0.5 divided by 0.5, which is 1. If we take 0, subtract a mean of 0.5, and divide by a standard deviation of 0.5, we'll get minus 0.5 divided by 0.5, which is -1. Therefore, we map 1 to 1 and 0 to -1, so this works. Next, we load in the MNIST train dataset from Torch Vision. You've seen this before. Next, we create a data loader from our dataset. Next, we create our discriminator network. So this is an ANN with layer sizes 784, 512, 256, and 1, and with leaky ReLU activations. Next, we create our generator network. This is an ANN with input dimension 100 and hidden dimensions 256, 512, 1024, and 784. Notice how we've also added a batch norm after each leaky ReLU, and that the neural network ends with a TANH activation, which maps the output values to be between -1 and +1. Next, we set the device to be the GPU, and we move both the discriminator and generator to the GPU. Next, we create our loss and optimizers. For the loss, we can use the binary cross entropy for both cases. The only thing that changes is the label. For the optimizers, we make sure to pass in only the parameters for that specific network. So the D optimizer only optimizes the parameters in the D model, and the G optimizer only optimizes the parameters in the G model. Next, we have a convenience function for scaling images back from -1 + 1 to 0, 1. This is useful for plotting and saving and so forth. Next, we create a directory to store the images generated during training. It's called GAN images. Next, we have the training area. So this will be slightly more complex than the code preparation section, since I left out a few minor details. But hopefully you understand the main idea, and so these minor details are just that, minor. So to start, we're going to create one-dimensional arrays just containing ones and zeros. These will be used as targets during training. The targets are constant values, so instantiating these inside the loop would be wasteful. Next, we create two lists to store the losses for the generator and discriminator. Next, we enter a loop that will go for 200 epochs, and inside that loop, we have another loop to go over the data loader. Notice we ignore the targets by using an underscore, since they are not used. Inside the loop, the first thing we do is get n, the batch size. Remember that since the batch size may not divide evenly into the total number of samples, the actual batch size may not be equal to the specified batch size. Next, we take the inputs and flatten them into an n by d matrix and move it to the GPU. And now that we have n, which is the current batch size, we can also index the ones array and the zeros array to get the correct size targets. Next, we have the train discriminator block. The first thing we do is get the loss for the real images. So we pass the inputs through the D model and call that real outputs. Then we pass real outputs into our criterion with ones as the target. We'll call this D loss real. Next, we calculate the loss for the fake images. So we start by generating some noise, which goes in a matrix of size n by 100. We move that to the GPU. Next, we create our fake images by passing this noise through the generator. Next, we pass the fake images into the discriminator and we get the fake outputs. We pass fake outputs into our criterion with zeros as the target. We'll call this loss D loss fake. Next, we combine the losses by taking the average. Then we zero the gradients in both optimizers. Then we call dloss.backward and then doptimizer.step to do one step of gradient descent on the discriminator. Next, we have the train generator block. As mentioned, it's been found that training the generator more than once for each iteration is useful. So we do a for loop that goes twice. Inside the loop, we generate some random noise of size n by 100 and move that to the GPU. Next, we pass this to the G model to get a set of fake images. Next, we pass the fake images through the D model to get a set of fake outputs. Next, we pass the outputs through the criterion, this time using ones as the targets. This is because we would like the discriminator to think these are real. Next, we do a gradient descent step. First, we zero the gradients. Then we call gloss.backward, and then we call goptimizer.step. And remember that even though the outputs that go into the loss function are outputs from the discriminator, we are running goptimizer, which only knows about the G model's parameters. So only the G model's parameters are updated. Finally, we save the losses to our list of losses. We print the epoch number and the losses. And then, at the end of each epoch, we save the fake images that were last generated using the save image function that we imported earlier. Note that before we save the images, we have to scale them back to the correct range using the scale image function. Okay, so let's check out the loss per iteration. So as promised, it's not the nice downward converging pattern that you're used to. Okay, so let's look at the images we generated. So here are the fake images after epoch 1. We can see that at this point, they are already starting to resemble the MNIST dataset. After epoch 50, it pretty much looks like MNIST. After epoch 100, it looks even more like MNIST. After epoch 150, it still looks like MNIST. Maybe even a little better. And after epoch 200, it still looks like MNIST. So, as you can see, the results are pretty much what we expect. At the beginning, we didn't see anything at all, and by the end, it looks pretty much like MNIST. The generator learns to generate real-looking digits quickly, so there's an aspect of diminishing returns here. After the first third of the way through, things already look pretty good.